Hello everyone, welcome to DrZ Academy. In today's video, we're going to move on to Chapter 5, Common Discrete Distributions. Alright, so let's firstly consider the first one. So, discrete uniform distribution. Okay, so what is a discrete uniform distribution? Alright, so let's consider the definition here. Let x be a random variable with support xx, sx, see this one. So where r is less than infinity. And the PMF is given as, alright, so P of xi equals 1 over r for each of them, right? So they are uniform, right? So their probabilities are all 1 over r. Then x is called a discrete uniform random variable on S sub x. And it's said to have a discrete uniform distribution on S sub x. Alright, so this is the definition for discrete uniform distribution. Okay, so now let's see this theorem about discrete uniform distribution. Let x be a random variable with a discrete uniform distribution, right, on this support, okay, x1 through xr. Then we have the following, all right, the expectation, the variance, and what? The moment generating function. Okay, so it's pretty easy to see that, right? So now, very easy to prove. For instance, expectation of x is going to be simply xi times p of xi, right? So, and you can see that it's a summation of xi 1 over r, because they're all 1 over r, so it is summation of xi over r, right? So that's what we have. And similarly, you can verify this is this one is what? Expectation of x squared minus the square of the expectation. That's easy. And the moment generating function, you can also find it, right? So x of t is expectation of e to the power tx. So, and you can see that's a summation e to the power txi times p of xi, right? So, and you can see that this is all 1 over r, right? So it's 1 over r. So that's summation of e to the power txi over r. So that's what we have, right? So expectation, variance, and moment generating function. So basically, with all these, it's pretty much everything we know about this discrete uniform distribution, right? So let's consider this example. Assume that we have 5 hats, A, B, C, D, E. It's known that these hats can jump up to 4.0, 4.5, 5.0, 5.5, and 6.0 times of their lengths, respectively. Alright, so if one cat, these are cats, not hats. Alright, if one cat is randomly selected, let x be the number of times its length it can jump up to, right? So now then find the expectation, variance, and the moment generating function, right? So now for this one, solution, right? Solution. Now you can see that based on this one, since a cat is randomly selected, right? So their chances is going to be exactly the same, 1 over 5, right? So 1 over 5. Okay. So x, we know x has a discrete, all right? So uniform distribution on, right, as x equals what? Right, so it should be 4.0, 4.5, 5.0, okay, and 5.5 and 6.0, right? So this is this one, right? Because it's randomly selected, right? So that's the support, and this is my random variable. Okay, so r equals what? 5. There are 5 cats, right? 5 possible values. So therefore we have that. Now then is A, find the expectation. It's going to be very easy, right? So expectation is simply what? Summation of all those xi over r. So it is going to be 4.0 plus 4.5 plus plus 6.0 over 5. Over 5, yes. So let's just take this summation, right? 4 plus 4.5 plus 5 plus 5.5 plus 6. So 25. 25 over 5, that's 5. Okay, so that is to say the expectation is 5. And we also have the variance, right? So the variance, the variance of x, right? So the variance of x equals what? As we know, the expectation of x squared, right, minus the square of the expectation. And from the theorem, we see that this is a summation of xi squared over r, right, minus 5 squared. Okay, so just to plug in, all right, so we can have 4.0 squared plus 4.5 squared plus plus 6 squared over 5 minus square root of 5 equals that, right? So let's just use a calculator again. 4 squared plus 4.5 squared plus 5 squared plus 5.5 squared plus 6 squared, right? So the summation divided by 5 and then minus 5 squared, right? So 25. Okay, so I got 0.5. Is that right? Okay, so 0.5. I got 0.5. All right, so that's what I get. Okay, so 0.5. And C here, right? So I'm finding moment generating function. So I'm going to write here. Okay, so instead C. So moment generating function of x equals, all right, so as we know, it's a summation e to the power txi over r, right? So which equals e to the power tx 4t, right, plus e to the power 4.5t plus e to the power what? 5t plus e to the power 5.5t and plus e to the power 6t and over 5. That's it, right? So that's going to be the moment generating function, right? So of course, from the moment generating function, you can find all the moments of x, right? So very good. All right, so that's about the discrete uniform distribution. Now let's move on to the next section. It's the binomial distribution. Okay, so this is in almost all actuarial science exam P exams, they will have binomial distribution. It's a very important one. Okay, so now let's start binomial distribution. Now, what is a binomial distribution, right? Before we introduce the binomial distribution, let's consider the definition so-called Bernoulli trial. So what is a Bernoulli trial, right? So a Bernoulli trial is a random experiment with only 2 possible outcomes, right? So of these 2 outcomes, we call the outcomes that we are concerned about success. All right, so one is called success, the other is failure. So success is usually the outcome we are concerned of, we're interested in. Okay, so that's called a success. And then the other called a failure. All right, so, but it doesn't really, success doesn't really always mean something positive, all right, something good. All right, so sometimes it's just something we are interested in. Okay, so you can see that flip a coin, right? It's a head or tail, right? This is going to be a Bernoulli trial, and you want to, whether it is the product is good or defective, right? So that's going to be a Bernoulli trial, right? So good, effective. Yes, so that's two possible outcomes. So we will call one of them success and the other failure. Okay, so the probability of success is denoted by P. All right, so denoted by P, and the probability of failure is going to be what? 1 minus P. Yes, 1 minus P. Okay. So now we consider this concept of binomial random variable. Okay, consider a random experiment consisting of n independent and identical Bernoulli trials. If you flip a fair coin, then all fair coins, right? So once, twice, 10 times, for instance, right? So it should be what? Independent and identical, all right? Bernoulli trials with a probability of success P. The number x of successes among these n trials is said to be a binomial random variable with parameters n and p. Okay, so denoted by this one. All right, x has a binomial distribution with parameter n and p. So here n is the total number of trials. All right, so number of trials involved in this experiment. All right, so P is the probability of success, right? So prob of success. Okay, in each trial, right? In each trial. Okay, so here, what is X? X is the number of successes among these n trials. Yes, among these n trials. So that's going to be a binomial random variable. Okay, so now let's consider this theorem about binomial distribution. Let X be a binomial distribution with parameters n and p, right? Then the PMF of X is going to be given below. Okay, so now here the support of X is what? 0, 1, 2, till n. That makes sense, right? So just think about it. If you flip the coin for 10 times, and X is the number of heads, now the possible values of X can be what? Can be 0, yes? So there is no head, all tails. Right? It may be 0, yes? And maybe 1, maybe 2, right? And till what? 10, all heads in that case, right? So X will be 10. So it's going to be from 0, 1 to 10, right? So in that example, but in general, we will say the possible values of X are 0, 1, 2, till n. Yes, so that's the support of this binomial random variable. Very good. All right, so now we have this one. Yes, very good. Now let's well, the probability, right? So the probability, now for each of them, now you can see that for this one, right? So y to the probability equals this one. So there are x equals x, right? Among these ones, they are independent. They're all independent. And also what? They share the same probability of success, right? So for P is a probability of success. There are x successes, and there are n minus x failures, right? So now this is for you select it's like a selection problem, right? So you select x among these n, right? So you just select x from these n trials, right? So for each trial, for each combination, the probability is this one. So you need to what? How many such combinations, right? So it's n choose x. So that is n choose x, right? So now this n choose x is what? Is actually, it can be, it's also ncx, or it equals what? N factorial over x factorial, n minus x factorial, right? So we can use a calculator to calculate this value as well. Yes? So that's about the binomial distribution. All right, so this calculator, right, we can find this DrZ X. Okay, very good. Now let's consider this example. Suppose 40% of the population in a large city own a house. 5 individuals are randomly selected from the city, and X be the number of individuals among them who own a house. Okay, so find, okay, so A, what is the distribution of X? B, find the probability, and these ones. All right, so now let's do this one. And now, solution. So you see that, right? So A, what is the distribution of X? Now, we can see that we are having 40% of the population in a large city own a house. 5 individuals randomly selected means what? They're independent. And since it's a really large city, right? So they are each one of them, each individual can be viewed as a Bernoulli trial with the same probability of success. So you have n equals 5, and P for each of them, the probability of owning a house is 0.4. So we are interested in the number of individuals among them who own a house, right? Among these 5 selected ones. So X has a binomial distribution with parameter 5, and P is 0.4. Okay, so that is the distribution of X, right? Binomial distribution. Parameter N is 5, P is 0.4. Very good. This is part of A, and then part of B. Okay, so we want to find the probability for X equals 3. Okay, X equals 3. Okay, so using this theorem, right? So the P of X, right? So that is P of 3, right? So N is 5. 5 choose 3. P, which is 0.4 raised to power 3. 1 minus 0.4 raised to power 5 minus 3. Okay, so now this is 5 choose 3. All right, so you can find this value here using a calculator. All right, so I'm going to 5 prob. Okay, go to N choose R 3. Okay, so it's 10. Okay, so it's 10 times 0.4 to the power 3, and then times this is 0.6 raised to power 2. All right, so now times 0.4 to the power 3 times 0.6 raised to power 2. Okay, so I got this one is, right, 0.2304. Okay, so that's question B. All right, that's question B. The probability for X equal to 3. And then for part C, probability for X less than 2. All right, so strictly less than 2. Less than 2 means what? It may be the support of this function is going to be what? Sx equals, since n is 5, so 0, 1, 2, 3, 4, and 5. Right, that's the support. Okay, so less than 2 means it can be 0 or 1. So it is P of 0 plus P of 1. Right, so again, 5 choose 0, 0.4 to the power 0, 1 minus 0.4 to the power 5 minus 0, plus, now, 5 choose 1, all right, so times 0.4 to the power 1, and 1 minus 0.4 raised to the power 5 minus 1. Okay, so you can just got this one, right? So this is going to be what? 5 choose 0 is 1, all right? 0 times, this is also 1, right? 0.4 to the power 0 is 1, and then that's 0.6 to the power 5, right? Plus, this 5 choose 1 is 5, 5 times 0.4, right, to the power 1, times 0.6 to the power 4. Okay, so let's use a calculator to find this one. 0.6 raised to the power 5 plus 2 times 0.6 to the power 4. and you got this is what? I got this one. So 0.33696. Right, 0.33696. Okay, so that's what we got for part C. All right, now let's see part D. Okay, part D. Okay, I'm going to write here. Okay, probability for x greater or equal than 4. So that's what? P of 4 plus P of 5. Yes, so P of 4, that's 5 to the 4, 0.4 to the power 4, 1 minus 0.4 raised to power 5 minus 4. That's the P of 4. Okay, then plus 5 to the 5 plus 0.4 to the power 5. No, plus. Okay, it should be times, right? 0.4 to the power 5, 1 minus 0.4 to the power 5 minus 5. Okay, so let me just erase this part. Okay, so this one equals 5 to the 4, that's 5 times 0.4 to the power 4 times 0.6 to the power 1, right? So plus this 5 to the 5 is 1 times 0.4 to the power 5 and times 0.6 to the power 0, which is 1, right? So times 1. So this one equals, okay, so 5 times 0.4 to the power 4 times 0.6, right? Plus 0.4 raised to power 5. That's it. Okay, so that's going to be what? 0.0704. Okay, so that's what we get for part D. Yes. Okay, so see, that's a example, right? That's about this example. You first need to know what's the distribution of x, right? What's the distribution? It's a binomial distribution with parameters. N is 5, P is 4. And after we got this, everything else is just using what? This PMF, right? This PMF. So, very good. All right, just be careful in the calculators, right? So you need to know how to use the calculator to do the calculations. Very good. Now, okay, now let's consider the moment generating function for the binomial distribution. Okay, so by definition, the moment generating function is going to be what? The expectation of this one, and now we use which equals this one, right? So this is e to the power tx times that one. So then it equals summation of x and x, p e to the power t raised to the power x, right? So e to the power tx is e to the power t then x, right? So and then just put them together here. Then it equals what? This is PET plus 1 minus P raised to the power n, right? So raised to the power n. So that's the moment generating function for the binomial distribution with parameter n and p. Now from this one we found, okay, the first derivative is going to be by using the chain rule, right? So n times this one, n power n minus 1, PET, right? So and then n PET, this one to the power n minus 1, right? So therefore the expectation of x equals what? First derivative, right? So at point 0, which is np, right? So this is going to be np. Then you can find the second derivative using what? This one is using the product rule, right? Using the product rule. So that's going to be, all right, so the derivative, you see, this is the first term, this is the second term, this is a product, right? So derivative of the first is the same times the second, plus the first times the derivative of the second, right? The derivative of the second is going to be here. Now, you can get this one, all right? So now, therefore, the expectation of the x squared, so the second moment, is going to be the value of the second derivative at point 0. Now, you can simplify that. It equals this one, all right? So now, therefore, variance of x is the expectation of x squared minus the square root of the expectation, plug in, right? So you get what? This is np 1 minus p. All right, you got np times 1 minus p. Now, therefore, we got the following theorem. So if x has a binomial distribution with parameter n and p, right, then the expectation is going to be np, and the variance is going to be what? Np 1 minus p. All right, that's exactly what we'll get here in the theorem. All right, so very good. Now let's consider this example. All right, say an exam consisting of 12 multiple choice questions in which there are 5 choices for each question. Right? Suppose that you randomly pick an answer for each question, that x denote the total number of correctly answered questions. Write an expression that represents each of the following probabilities. Okay, well, anyway, so what is the distribution of x? Right? So firstly, what is the distribution of x? Find the expectation variance, find the moment generating function. All right, so let's just do this one. Firstly, what is the distribution of x? All right, A, right? So what is the distribution of x? So you have 12 multiple choice questions, right? Now 5 choices for each. Only 1 is correct. Okay, so only 1 correct answer. So already assume that only one is correct, or only 1 is correct. Okay, so let's say that. So suppose that you randomly pick answer for each question. So if they're independent and they have the same probability of getting success, right? So now n is gonna be what? 12 multiple choice questions. And p, the probability of success is 1 over 5 is 0.2 because only one of these 5 choices is correct, right? So if you randomly select 1, that's 1 out of 5, which is 0.2. So the x has a binomial distribution with parameter is 12, and this is 0.2. Okay, that's part A. And the part B, right? So what's the expectation? All right, so the expectation is going to be what? NP equals 12 times 0.2, which is 2.4. Okay, 2.4. Okay, sorry. 2.4. Okay, so and the variance is. Alright, so variance of x is np 1 minus p, right? So that's 12 times 0.2 times 1 minus 0.2. Okay, so now you can find this one, right? So, alright, 2.4 times 0.8 is 1.92. Okay, so 1.92. Okay, so that's the variance of x. Okay, so part A and B. And then for C, all right, so find the moment generating function xt, right? So as we know, this is also, right? So we know that it equals what? In the parentheses, right? P e to the power, this one, right? P e to the power t plus 1 minus p to the power n. So that is the formula. So p is 0.2, so 0.2 e to the power t plus 1 minus p is 0.2 raised to power n is 12. So this one equals, right, 0.2 e to the power t plus 0.8. All right, so raised to power 12. Right, so that's going to be the moment generating function for this random variable. Very good. Okay, so you can see, right? So as long as you identify the distribution, right, n and p, right, the binomial distribution with parameter n and p, then you can just use their properties, right, to find the expectation, to find the moment generating function, the variance, and some probabilities, right? So but the key is to identify the distribution of X, right? So all right, so I think that's pretty much about this video, and thank you so much for watching. And if you feel like this video is helpful, please click on the like button. And if you think this video will benefit some of your friends, please feel free to share it with them. Thank you very much, and I will see you in the next one. Bye bye.